Hello, everybody. I hope you are ready for another exciting round of CHY 113. Last time we focused in on really looking at the specifics of bonding and how to differentiate if two atoms are going to bond covalently and share their electrons, ionically and transfer their electrons, and so forth. And from there, we started to narrow our focus more on covalent molecules and looking at how they're really going to come together. And we spent a lot of time with Lewis structures. And so today I wanted to start out with some Lewis structure practice. And so there are several different molecules that I want you to go ahead and draw the Lewis structures for. NH3, H2O, CH4, and XeF4. Apply the rules for Lewis structures that we went over last time. Feel free to pull the rules out, have them right in front of you as you're doing these structures if you want. And so go ahead and pause the video now, and then come back and we'll go over each of these different structures. And so our first was NH3, ammonia. And it was a fairly straightforward one, so hopefully you were able to come up with this structure for ammonia, nitrogen central with one lone pair on it, and the 3 hydrogens surrounding that nitrogen. And then we have our structure for water, our oxygen in the middle with 2 lone pairs and the 2 hydrogens on the ends. Our structure for carbon tetrafluoride, central carbon, the 4 fluorines surrounding the carbon. And it is important to note the 6 electrons around each fluorine, the 3 lone pairs around each fluorine atom. Those are vital when doing your Lewis structures. If you do not have those lone pairs, your Lewis structure is incorrect. We must be accounting for all of our different valence electrons in these structures. And the last one, xenon tetrafluoride, that one might have thrown you a little bit, depending on if you've watched the video about expanded octets. And so, again, we have our xenon central, our fluorides are surrounding, we have our lone pairs around each fluorine atom. When we filled the octets around fluorine, though, we still had 4 electrons left over, which had to go somewhere. Those electrons are going to go around xenon. Remember that any atom that is larger than phosphorus, so anything that's actually phosphorus or larger, can have what we call an expanded octet if it needs to. So if you still have more electrons to place and you have nowhere to put them around the outer atoms, as long as that central atom is at least phosphorus or larger, we can have more than 8 electrons around that atom. And that's what we end up with here with xenon tetrafluoride. And what we're going to find, what we're going to see today, is that those lone pair, that lone pair on xenon, or these 2 lone pairs on xenon, are actually going to, sorry about that, are going to have a large effect on the overall 3-dimensional shape of that molecule. And so it's key to put those there. If you don't have those there, you won't be able to assign the correct shape to xenon tetrafluoride. And so those are very important. And that's where we're leading into today, is to be able to take all of these different Lewis structures and many, many more, which we'll talk about, but to be able to take these Lewis structures and use those to assign a 3-dimensional shape to the molecule. Because as it turns out, which we'll be talking about a little bit later in the semester, the shape of the molecules has a huge role in establishing some of the properties that the molecule is going to have. And so we have to be able to identify the shape, and that's where we come to today. One thing that I would highly recommend as you go through this lecture, and as you sort of go through your studying for this material in general, go to this website right here. It's a PhET site. For those of you that aren't familiar, the University of Colorado puts out some incredible interactive material they've got some chemistry, some biology, some physics material, all sorts of great stuff. And so this particular site we're going to use to help us visualize our molecules in 3D. If you have model kits, I mean, I've got a bunch of different models here that I'll be showing throughout the lecture as well. This is what model kits are great for. So you can actually see the molecule in 3 dimensions, rotate it around, play with it a little bit. Those of you who are eventually going on to organic chemistry, I highly, highly, highly recommend that you purchase a good model kit. They are pricey. Good ones are going to run you 40, 50 bucks. But I can't stress enough that especially when you get to OChem, being able to actually hold the molecules in your hands and really look at them in 3D is going to help you with a lot of the different concepts you study in there. So that's just something to keep in mind. But this website here does do a great job as well. We'll just sort of take a peek at it here. Actually, let's take a look at a real molecule instead. And so we can see here, and we're going to be talking about all of this, but we can see here a molecule of water, for instance, and we can really start to check out the three-dimensional shape of it. And this program as well, or this simulation, allows us to see the lone pairs that are on the oxygen atom. So remember here we go with our Lewis structure for water. So these are our hydrogens in white, our oxygen here in red. And these lone pairs, we can visualize here as well, which will play a role, again, in the three-dimensional shape of the molecule. If we don't want to see the lone pairs and just the atoms, then we can see and we can spin this around and we can really just sort of check out the molecule in 3 dimensions. So this is a fantastic simulation. And again, I would highly recommend that you have this up as we're working so that you can build the molecules in here yourself, spin them around, play with it a little bit, and try to see what these things really do look like in 3D. It will benefit you. And so, okay. And so let's start talking about shapes. Lewis structures give us a really good indication for how atoms are actually connected. We can see in the case here, for instance, of methane, we have a central carbon atom with 4 hydrogens surrounding it. And that tells us how everything is actually hooked up. Likewise in our other Lewis structures. And these were all fairly simple ones that we had looked at, but we're able to see, for instance, that we have a nitrogen with our 3 hydrogens surrounding it, carbon with our 4 different fluorines surrounding it, and so forth. And so the Lewis structures tell us how things are actually connected. The actual 3-dimensional shape of the molecule, though, is going to be determined by what we call the bond angles. A bond angle is, just as the name implies, if we take 3 different atoms within a molecule, we're looking at what the angle is that those 3 atoms make. And here's a great example. We can see this one here as we start to talk about some of this. When we look at the Lewis structure for methane, and this would be a good representation of methane here, with our carbon in the center, our 4 hydrogens surrounding it. If we just look at the Lewis structure as the molecule is drawn flat on our paper, that would suggest that these angles here, the hydrogen-carbon-hydrogen angle, looks like it's just 90 degrees. Right? That's the way it's drawn, that's the way it's written, that's what it looks like. However, experimental evidence tells us that that bond angle is actually 109.5 degrees. We're not going to worry for this class about how that's found, but just trust me that experimentally we have determined that that angle is actually 109.5. But if you remember your geometry a little bit, there are 360 degrees sort of like in a full circle. And so again, if we sort of look back here, if each of these were 90, yeah, there we go. We'd have 4 of them, 360 degrees, and that would make sense in this 2-dimensional world. But we know that they're each 109.5. And so it can't be just this 2-dimensional, 2D flat thing on paper because the angles don't add up. The angles aren't going to add up right. And so that tells us that the methane molecule, the way the molecule actually appears in real life, must be 3D. It's got to have 3 dimensions to it, rather than just this flat 2D on paper sort of visualization. And that's what we really see. This is what the shape of methane really would look like in order to attain that 109.5 degree angle. And so the way that we actually visualize that on paper, the way that we write that on paper, is by using what we call a dash and a wedge drawing. And so the way that the dashes and wedges work is anything, you can sort of visualize the plane of the paper, of the board, whatever you're working with. Anything with just a standard line is within that plane. And so here's our methane here. We have our carbon here in the middle. This, and I'm trying to hold this as sort of as flat to the screen as I can. This hydrogen and this hydrogen are within this plane, are within the plane of the paper, so to speak. And so they would represent these two here. Anything with a wedge visualizes coming out at you. And so this wedge right here is coming out of the screen. This hydrogen is coming down a little bit from the carbon, but is also angled towards you, out of the screen. That would be this hydrogen right here. And you can see, hopefully you can see from in the video, that this hydrogen, again, is sort of pointed down, but is also coming at you. It is directed towards you. And then we have this dashed line here. This, again, this sort of pointed a little bit down, but is going back behind the screen. So if you're watching this on a computer, on your iPhone, whatever, picture that as being in behind. That hydrogen is in behind the screen. It's the one that I'm actually holding, which you can't see because it's behind everything else. And so we have this three-dimensional shape now of the methane molecule. It's a shape that we call tetrahedral, and we're going to talk about all of these shapes. And we can see just an even bigger visualization of it here. Same idea. This is carbon tetrachloride, but it adopts that same tetrahedral shape where we have two chlorines that are within the same plane. So carbon, chlorine, chlorine. So those are all within the plane of your screen. This chlorine is coming out at you. This chlorine is going back away from you, in behind the screen. And so the question then becomes, okay, well, how do we determine this? How do we actually determine the shape? We use what we call VSEPR theory, valence shell electron pair repulsion. And so maybe the question you're asking yourself, or hopefully a question you're asking yourself is, okay, well, how come? Why does something like methane or carbon tetrachloride adopt this shape? We have to remember that electrons are making up these bonds. And let's just come back to here for a second. So electrons are making up these bonds. Electrons, remember, are going to repel each other. They're negatively charged. And so if the molecule was simply in two dimensions, was just in 2D, with these just being 90 degrees and everything being within the same plane. So when I say 2D, picture maybe the carbon here in the middle of my hand. And then actually I'll do it like this. The carbon's right here in the middle of my hand, hydrogen here, hydrogen here, hydrogen here, hydrogen here. So again, all just within the same plane. And so if everything's in the same plane with just 90 degrees in between each element, that doesn't maximize the space available so that the electrons can get as far apart from each other as they can. This conformation does. So now that we've adopted this three-dimensional conformation, now the electrons making up these bonds can actually separate as much as they can. That's the R in VSEPR theory, repulsion. The electron pairs are going to repel each other. And that's what gives rise to our three-dimensional shape. Also, sorry, let me check something real quick. Okay, I thought it looked like my video had got cut off, or my graphic was cut off, but it's not. And so there are two different terms that we're going to work with throughout this unit. We're going to discuss molecular geometry, which is the actual shape when we consider just the atoms around our central atom. When we talk about shapes, we're always going to be talking about the shape around our central atom, the shape of the atom in the middle of the whole thing. And so when we say that this molecule, for instance, is tetrahedral, we're saying that this is tetrahedral around this carbon atom. Let's just actually come over to the PhET application real quick. And so if you were modeling, just to show you how to use this, and so if we start from scratch here, we have just one atom in the middle. And what you can do is if you're clicked onto this atom, you can select what type and how many bonds to place on it. And so if we're trying to model this molecule right here, we're going to have this, our atom right here in the middle. This is our carbon, connected all with single bonds. So there's one bond, And there's our 4 bonds on it now. I just clicked it 4 times to add 4 different bonds on there. Now that I have that molecule, I can start to rotate it around and look at it in 3 dimensions. And so that's how you use this program. Play with it a little bit, and really look at how it works. You can also show the bond angles if you want. And so we can see those here if we click this. And we can also, we're going to start getting into the naming and how we name the shapes. You can also show that actual name down here if you click these boxes as well. And so we'll work with this as we go. I just wanted to introduce it and really show it now, how you actually use it, so you can build some of these within the platform as we go. Okay. And so we're going to define both the molecular geometry, which is the geometry that the actual atoms within the compound have. We're also going to talk in terms of electron pair geometry, which takes into account the atoms and any lone pairs that might be around the central atom as well. And so in the case, for instance, when we looked at water, let's bring it back here to water. And so we would have, try to rotate this in such a way that we can really see what's going on here. Okay, close enough. So we've got 2 different geometries, and we're going to be talking about these and going over these, but we have 2 different geometries here. We have the geometry of all of the electron pairs around our oxygen. And when we look at the electron pairs around our oxygen, we have 2 that are here in bonding pairs. They make up our bonds to hydrogen. We also have 2 lone pairs around the oxygen. And so that's going to give us, and again, we're going to talk about all these. I just want to differentiate between electron geometry and molecule geometry. That's going to give us an electron geometry of tetrahedral, because we have 4 different pairs of electrons around our central atom. If we want to look at just the actual atoms themselves, though, it's taking the lone pairs away. Now we're looking at just the geometry of the atoms themselves. That's our molecular geometry. In this case, the molecular geometry is going to be bent. And again, we're going to look at how we actually determine these and our tools to use to determine these names. But this is just to show us our difference between just our straight up molecular geometry of the atoms, but also the electron geometry that takes into account all electrons around that central atom. And so let's just sort of go through and build up from scratch. And so we have several different types of electron pair geometries. If we have 2 pairs of electrons around our central atom, then that's an electron pair geometry of linear. Now, again, we're only looking at electron pairs now. We're not differentiating between if that electron pair is a lone pair or an actual bonding pair to another atom. So we have 2 pairs of electrons around our central atom. We call that an electron geometry of linear. 3 pairs around our central atom, trigonoplanar. 4 pairs around our central atom is tetrahedral. 5 pairs around our central atom, trigonal bipyramidal. And finally, 6 pairs around our central atom, octahedral. Now, obviously, in these last 2 cases, trigonal bipyramidal or octahedral, we would have to be working with central atoms that are phosphorus or larger so that we can meet our expanded octet. And so when we talk about these electron domains, these regions where we find electrons, like I said, we've got, and like we've talked about before, we have either bonding pairs or non-bonding pairs. Bonding pairs, and this is important for what we're going to be talking about here, when we're talking about the VSEPR theory and molecular geometry, it doesn't matter how many bonds we have. One region where we find electrons is we consider to be one electron domain. Doesn't matter if it's a single bond, double bond, or a triple bond. And so, in other words, if I'm looking at, sorry, let's just do this. So right here, I've got two different atoms around, or two different bonds here around my central atom. And so this would be a linear electron geometry. And I've got 1, 2 electron domains. And so that's what we're counting up, is how many regions around the central atom do I find electrons? Now I've got 2 double bonds around my central atom. This is still only 2 electron domains. There are 2 regions where I find electrons, and that's it. If I had something like this, which is possible, now I've got 4 electron domains. 2 of them are bonding, and this is one of the things that we're going to have to start to differentiate. 2 of these are bonding domains. 2 of these are non-bonding domains. So I have 4 total electron domains around my central atom here. 2 of them are bonding, 2 of them are non-bonding. And again, we're not taking into account whatsoever the fact that these are double, single, or triple bonds. It's just 2 areas where we find electrons. And so we've talked about this a little bit already, that the electron domain geometry is the arrangement of all of the electron pairs, whereas the molecular geometry is the arrangement of the atoms. Now, what we're going to see as we work through these, we're going to work through all of the different electron domains and the different molecular domain geometries that those can give rise to. But one of the things that we're going to see in one of the patterns that you'll notice as we work through this is that if the central atom does not have any lone pairs, does not have any non-bonding pairs, that's going to mean that the electron domain geometry and the molecular geometry are the exact same for that molecule. And that should make sense. Let that percolate in your heads a little bit and see if that just makes sense to you. Okay, so actually I'm going to pause the video for just a second. Remember Rangeley, who popped into our last video. He is outside right now, and it is a cold morning, so I'm just going to go upstairs and check and make sure he doesn't want to come in. I'll be right back. He did indeed want to come in. He wanted to come say hi to everyone again. Here he is. Hi, everyone. All right. Go on, kitty. Okay. So let's start going through our various electron domains. Now, our simplest is just going to be if we have 2 electrons around our central atom, or sorry, 2 electron domains around our central atom. The only way that we can do that, or the only situation where we're going to have that, is if both of those, actually, let me back up. So the way that a chart like this works, something like this here, and this is very similar to the chart that you're going to be able to use. Let me actually pull that up now. If you go to the website, go under Unit 3, Bonding and Molecular Structure, get this VSEPR chart. This is something that there are several different versions of VSEPR charts out there. This is one that I put together a year or so ago that I really like. You will be able to use a version of this on your exam. The version that I'm going to allow you to use just doesn't have these examples on it. But you will be able to use something like this on the test. The way that this works, so we use a VSEPR chart like this to help us determine what the electron geometry and molecular geometry is of a molecule. The first thing that we have to do is identify the number of electron groups around the central atom. So we find our central atom, and we determine just simply how many electron domains. You can see if I can blow this up a little bit. There we go. We determine how many electron domains are there around that central atom. The next thing that we have to do is identify how many of those electron domains are bonding versus non-bonding groups. So how many of them are involved in single, double, or triple bonds for our bonding groups. Remember that each type of bond still just counts as one, doesn't matter what kind of bond it is. And so how many of those are bonding groups or how many of those are lone pairs? And that will tell us what our electron geometry and our molecular geometries are, which also gives rise to telling us what the bond angles are in between the atoms in the molecule. And so our simplest is just 2 electron groups around our central atom. And so a case maybe like this of CO2. So here we have our carbon central. So there's our central carbon atom, oxygen on either side. And I'd encourage you to do the Lewis structures of these so that you're able to see this for yourself. So we have CO2 right here, or like in this example, CS2, carbon disulfide, same idea. 2 bonding groups. We do have 2 double bonds around on the carbon. Each of those are just 1 electron domain. So we have 2 electron domains here. Both of those electron domains are bonding domains, 0 lone pairs. That means that our electron geometry is linear, and our molecular geometry is also linear. And so no bonding pairs, so our electron geometry is identical to our molecular geometry. And linear, again, hopefully just makes sense to you. I mean, this, if we were to actually look at this molecule and see it, we would see that it is just a straight line, all 3 atoms lined right up. And so our bond angle, our oxygen, carbon, oxygen angle there is 180 degrees. And so there's our simplest electron domain geometry, with only 1 molecular geometry within that electron geometry. Next, we have examples of 3 electron domains. So now is where we're going to have to start to look at bonding versus non-bonding. In our simplest example of this, sorry, I shouldn't even say our simplest example. In one of our examples, so here we have 3 electron domains, 1, 2, 3. All 3 of those are bonding. None of those are non-bonding. And so our electron geometry is trigonoplanar. You'll see that we also have another trigonoplanar electron geometry. In this example right here, now we still have 3 electron domains. We've got 1, 2, 3 electron domains. 2 of these are bonding. This represents a lone pair. This is a non-bonding pair. We still have 3 electron domains though. So our electron geometry of both of these is going to be trigonoplanar. But we can see that our molecular geometries are quite different when we look at just the atoms. The molecular geometry of this is also trigonoplanar. And I hate to use this analogy, although these are coming out of fad, I guess, now in the last couple of years, but this would be your fidget spinner. People were using these a lot a couple of years ago, not these, but using something similar. And you can think of it as the same sort of idea. So trigonoplanar, all these atoms are within the same plane, but they're kind of fanned out in a triangle. All of the electrons are fanned out in the same plane here, but the molecular geometry, the shape that the actual atoms take, pop that out, is much different, is a bent geometry. Let's just see what each of those look like within the program too, so you can just get another idea of it. Let's just go ahead and reset. We'll reset this completely. So we're going to go with 1, 2, 3. So again, here we have we can see again, all in the same plane, spin it around a little bit, play with it. And so our electron domain geometry is trigonoplanar. Our molecular geometry is also trigonoplanar. Now, however, if we remove our double bond and add a lone pair on instead. So again, here we can see that our electron geometry is still trigonoplanar, all in the same plane, but our molecular geometry, looking at just the atoms themselves, the lone pair is still here. I'm just not going to visualize it. I'm going to take away the visualization, but it's still there. There's our molecular geometry we call bent. So that's how we use this chart. That's how we use this VSEPR chart. And so we can start to see where it is so important to have a correct Lewis structure. Let's take a look at our next example. Then we'll compare back to some Lewis structures. So now we move up to having 4 electron domains around our central atom. If all 4 of those, 4 electron domains around our central atom, no matter how many are bonding or non-bonding. If we have 4 electron domains around our central atom, our electron geometry is tetrahedral. So we have 3 different examples of that. In the first example, we have no lone pairs. All 4 of our electron domains are bonding pairs. And so that means that our molecular geometry is also tetrahedral. And so that would be, wrong chart. So there we go. Oh, let me get rid of our lone pair. There we go. So there's our tetrahedral shape right there. Tetrahedral electron domain geometry, tetrahedral molecular geometry. Now I'm going to remove one of our bonds and replace it instead with a lone pair. So that's this example here. This is NH3 that I'm holding in my hand right here. And so now we still have an electron geometry of tetrahedral. We still have 1, 2, 3, 4 electron domains around our central atom. But now one of those is a lone pair. And so our electron domain geometry is still tetrahedral, but now our molecular geometry is what we call trigonal pyramidal. And we can see that here. Again, same idea. This lone pair is still there. I'm just going to take it off for the visualization so we see just the atoms. It looks like this. And that's our 3-dimensional shape. And again, we can really see that here in the visualization if you spin it around. And again, I really, really encourage you, if you're not, to pull up this program and do this yourself as we're working through these. I think it will really help you visualize things. But next, I'm going to go ahead and remove one more bond, and we're going to have 2 lone pairs around our central atom instead. One more, there we go. So now we've got 2 lone pairs around our central atom, still tetrahedral electron domain geometry. So we still have a tetrahedral electron geometry, 4 electron domains around our central atom, but now 1, 2 of those are bonding and 2 of those are lone pairs. So that's going to give rise again to a molecular geometry that is bent. This would be water. So this is an example here of a water molecule, where we have 1, 2, 3, 4 electron domain geometries for an electron geometry of tetrahedral, but 2 of those are lone pairs. So the actual molecular geometry is bent. So it would look like that when we're looking at just the atoms. And so let's go back to the Lewis structures that I had you draw for our warm-up real quick, and we'll start to see why it's so important to get these accurate. So you look at these 3 here. So if we look at ammonia, water, and carbon tetrafluoride, all 3 of these have a tetrahedral electron domain geometry. The electron geometry on all 3 of these is identical. However, because we have no lone pairs on carbon tetrafluoride, 1 lone pair on ammonia, NH3, 2 lone pairs on our central atom for water, that's going to make the molecular geometry of all 3 of those very different from each other. The electron geometry is identical. They all have a tetrahedral electron geometry. But now they have very different molecular geometries. The atoms themselves take on a different shape due to that lone pair. It ends up making a huge difference, which will end up having a huge difference in the various properties that the 3 of these are going to have. And so it's vital to get our Lewis structures correct with the correct number of lone pairs. That's why drawing in the lone pairs is so important, because we use that to then determine our electron and our molecular geometries. And so let's just keep going through the others. Then we get up to 5 electron domain geometries. So now again, we're talking about atoms that for our central atom that are larger than, or that are phosphorus or larger. So if we have five electron domains, our electron geometry is what we call trigonal bipyramidal for all of those. So here, 3, 4, 5. So it's a shape that looks like something like this. Trigonal bipyramidal, because we can sort of visualize there being two different pyramids on this, so to speak. And visualize like one of them here, one of them, yeah, if you invert it a little bit, it can be tough to see. But it's called a trigonal bipyramidal electron geometry. And if all 5 of the electron domains are bonding, then again, it's also a trigonal bipyramidal molecular geometry. We get rid of one of the bonds and replace it with a lone pair. Now we have what we call a seesaw shape. So still a trigonal bipyramidal electron geometry. There it is. Now you can sort of see that it looks like a seesaw. And we have an example of that right here. So here's your seesaw. You're 6 years old again, out on the playground. Your seesaw going up and down. And then I'm going to get very politically incorrect. Oh, now the fat kid joined us. Now we're in trouble for a while. Sorry, that was very rude. It's okay. I was the fat kid, so that was me in elementary school. But there's our seesaw shape. Yeah, so one lone pair. Still an electron geometry of trigonal bipyramidal. We lose one more bond, add another lone pair. Now we get what we call a T-shaped molecule. So again, 5 electron domains still, so it's still a trigonal bipyramidal electron geometry, but the actual molecular geometry is T-shaped. It's pretty easy to see where that name comes from. Lastly, in this electron domain, now we add in a third lone pair, and now we see that we get a molecular geometry, once again, of linear. So all 3 of those lone pairs are in what we call an equatorial position, and we'll talk about that a little bit in our next electron geometry. And then we have the axial positions for our actual atoms, forming our linear shape. And so then finally that brings us to our last electron domain geometry. So let's take a look at adding in a 6th electron domain. Now we have what we call an octahedral electron domain geometry. So we can see our 6 different bonding groups around our central atom. And so we can see that here too. Now we also want to define, like I mentioned last time, we want to go ahead and define what we call axial and equatorial positions. I'm just bringing up to see, it's tough to see it in there too. It's okay. So we can see if we visualize the molecule like this. So visualize it just up and down. Actually, let me even put some different colors on here to make this a little bit easier to see. I should have thought ahead. Let's take our oranges off and add these blues on instead here. Okay. So when we start to look at in fact, even trigonal bipyramidal or especially octahedral, we also want to consider the positions that they're in. We just have so many different atoms around here now that we want to start defining some of these positions. And so we have our 6 electron domains. These 4 here, when we visualize holding the molecule like this, these 4 here, sort of if we imagine spinning it around like this, these 4 are in what we call the equatorial positions. And so you could visualize those as being, if we sort of picture the central gray atom here as the Earth, as the name implies, those would be along the equator. Versus the blues here are what we call our axial positions. And again, sort of thinking of this maybe as the Earth, those would be at the poles. So we're spinning around, we have our equatorial and our axial positions. Those are just some terminology to be aware of. And so here's our octahedral electron domain geometry. If we remove one bond and have a lone pair, now we have an octahedral electron geometry still, but we have what we call a square pyramidal molecular geometry. And you can sort of see where that name comes from. We have a square maybe making up the base. And if we visualize lines going up here or sides, then we can see that this would sort of form a pyramid with a square base. So that's where that name comes from. And here we have our equatorial positions with all the atoms. Lone pairs will typically, will always take up axial positions. There's more room there for the lone pair. Lastly, this is our very last one. If we remove one more bond and add in one more pair, we get what we call a square planar molecular geometry. Once again, still an octahedral electron geometry, still 6 electron domains around our central atom. But now we have a square planar molecular geometry because all of the actual atoms are within the same plane. Sort of spin it around. See if I can get a good, there we go, just like that. All within the same plane. This should maybe look semi-familiar. There's our XeF4. Our xenon tetrafluoride would actually end up with a square planar molecular geometry. Now let's just use our chart a little bit. Actually, let's use the chart we've already looked at these examples, but let's use our VSEPR chart, see how we would actually use this once again in determining the shapes of these molecules that we did in the very beginning. And so we started with NH3. And so when we look at NH3, we need to identify, when we look at any of these, we need to identify how many electron domains are around our central atom. So when we look at NH3, we can see that we have 1, 2, 3, 4 electron domains around nitrogen. So that tells us that we're going to be down in this region right here. And that tells us that our electron geometry is tetrahedral for ammonia. Because we have any compound with 4 electron domains has a tetrahedral electron geometry. But then we see that 3 of those are bonding domains and 1 of those is a non-bonding domain. And so 4 electron groups total, 3 bonding, 1 non-bonding, tells us that our molecular geometry is now trigonopyramidal. And so let's do the same thing with water. H2O, 4 electron domains. We have 2 bonding pairs, 2 non-bonding pairs, but it's 4 electron domains. And so our electron geometry is still tetrahedral, but our molecular geometry, so 4 bonding domains, 4 domains total, 2 bonding, 2 non-bonding, gives rise to a bent molecular geometry. CF4, we apply the same logic, 4 electron domains, and so we have an electron geometry of tetrahedral. All 4 of those are bonding. There are no non-bonding domains. And so our molecular geometry also tetrahedral. Finally, xenon tetrafluoride. We have 1, 2, 3, 4, 5, 6 total domains. Tells us that our electron geometry must be octahedral now. Just running out of space a little bit. octahedral. 4 of those are bonding, 2 of those are non-bonding. So again, 1, 2, 3, 4 that bonding domains, 1, 2 non-bonding domains. And so our, there we go, molecular geometry is square planar. That's how we use our VSEPR chart. Identify how many electron domains are around the central atom. That will give you your electron geometry. Then determine how many of those domains are bonding versus non-bonding domains. That will give you your molecular geometry. Once you know that, that will also tell you the bond angles that we see. You'll see in some of these too. Let's look especially here at our tetrahedral bonding domain, or our tetrahedral electron domain. It turns out that that lone pairs, non-bonding pairs, actually take up a little bit more space than non-bonding pairs do. Sorry, than bonding pairs. So let me just say that again. Lone pairs or non-bonding pairs take up more space than bonding pairs. What that's going to do is, so if you remember, and we can see on the chart, that our typical tetrahedral bond angle is going to be 109.5 degrees. So this bond angle right here is going to be 109.5. When we have instead a trigonal pyramidal compound with one lone pair, this lone pair takes up a little bit more space, and it's going to squeeze these down a little bit compared to what they would be in a tetrahedral molecular geometry. And so we say that this bond angle is going to be a little bit less than 109.5. And I'm not sure, let's see if the program might actually tell us exactly. With a lone pair, we see our bond angles. Now, this unfortunately isn't sophisticated enough to tell us that it's a little bit less. It's just going to give us the, sorry, and I haven't played with that yet, so sorry that I'm just learning that now. Here we go. So just know that the lone pairs take up a little bit more room. And so that's why you see this less than symbol, because the bond angle here is going to be a little bit less than 109.5 because there are atoms are squeezed down a little bit due to the lone pair. And we see that even more when we go to the bent molecular geometry with an electron geometry of tetrahedral. These 2 lone pairs on top just bend us down even more. I mean, certainly not to this extreme, but just to give you an idea for what's going on. We'd go from something like this, which would be our 109.5, to now those atoms are going to be squeezed down a little bit and create bond angles that are now getting less than 109.5. I mean, it's not extreme. Off the top of my head, if I remember right, you get something like usually like 107.5 or so for here and 104 or so for these. So it's not a huge effect, but we do have some effect of those bond angles. We also want to be mindful of our bond angles with trigonal bipyramidal complexes, because we do have different bond angles between our equatorial and our axial atoms. And so we see here, for instance, so here we can see it. So here's our trigonal bipyramidal complex. And again, we can sort of see the 2 different pyramids, pyramid up here and a pyramid down here. We have a bond angle between the equatorial atoms. So this bond angle from this atom to here, this bond angle is 120 degrees. But this bond angle is 90 degrees. So we do end up with different bond angles in trigonal bipyramidal and actually only in trigonal bipyramidal because they're all 90 degrees in octahedral. But we do have different bond angles in trigonal bipyramidal between our equatorial and our axial positions. So another thing to just keep in mind. So, okay, so that takes us all the way through. These are just several examples. I'm going to sort of just blow through these because these are just some examples of, we've already done this. I'm just going to kind of go through these real quick. So we have another major topic to talk about. Okay. So that's how we determine the shape of the molecules. Now, it turns out, though, that so a lot of the properties of these molecules are determined by the shape. But the other thing that's going to play a huge role is the electronegativity difference between the different atoms. And so let's say, for instance, so here we had something that was maybe just like methane, although typically we use white atoms or white for our hydrogens. I'm actually going to be a pain and change those. It's only a pain to me, but it'll take a second to do it. This will help illustrate the point, and I just want to be picky. Drop the hydrogen. There we go. Okay. So let's say instead of all the same type of atom, let's say instead we have one different atom. So this would be maybe, we can even look at the Lewis structure. This might be, for instance, CH3Cl. So we would have carbon, hydrogen, 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 chlorine. Now again, this is also a good illustration of the fact that our Lewis structures do not give us any information about the shape, or they don't represent the actual three-dimensional shape. Looking at the Vesper model or looking at models like this, now we start to see the shape. The Lewis structures simply show us how the atoms are connected. But let's think about this a little bit. So here we have CH3Cl. Our electronegativity difference between carbon and hydrogen is not enough that we're going to worry about. We're going to say that basically our carbon and our hydrogens, when we think about these two electrons that make up the bond, the carbon and the hydrogen share those two electrons equally. Remember when we looked at electronegativity difference, let's see. Oh yeah, so I've got this slide coming up, but let's go back to a slide that we looked at last time. We'll just make note of what number I'm on now. Okay, sorry, 102. I'm gonna go way back. Here we go. So remember we talked about these differences in electronegativity last time? We talked about the sort of continuum here, where if we only have an electronegativity difference between 0 and 0.4, we consider that to be what we call a purely covalent bond. The electrons are completely shared equally throughout that compound, or throughout that bond. If we start to get an electronegativity difference of more than 0.4, so call it 0.5, of 0.5 to 2, now we call that a polar covalent bond, where one of the atoms in there is going to be hogging the electrons in that bond more so than the other atom. This is huge when it comes to the properties of a molecule. And so let's think about that and come back to this example here. And let's bring our electronegativity slide back up. And so for each of our 3 carbon-hydrogen bonds here, we've only got an electronegativity difference of 0.3. Oh, sorry, I just threw 2.2 on this. I've seen 2.1 for hydrogen a lot. But an electronegativity difference of 0.3. So not enough of a difference. We consider this to be a purely covalent bond. These two electrons are pretty much completely shared equally between our carbon and our hydrogen. However, we have an electronegativity of chlorine. That's what this green atom is here. Remember, this is a chlorine atom. Chlorine has an electronegativity of 3.2. Carbon has an electronegativity of 2.5. Difference of 0.7. That's above our threshold to be considered a polar covalent bond. And what that means is that these two electrons that are making up our bond here between carbon and chlorine, these two electrons are going to spend more of their time up around the chlorine atom. This is huge. This is really, really big as far as the properties. Because what that's going to do is that's going to make this chlorine start to sort of kind of appear to have a negative charge. Not a full-on negative charge like a chloride ion would, like a Cl minus. It's not anywhere near that extent. But the electrons are spending enough of their time up around here to make it seem like chlorine kind of, sort of, is a little bit negative. And we've talked about the definitions of electronegativity, ionization energy, and electron affinity. We've looked at a little bit. Sorry, yeah, that was in our periodic trends that I didn't actually lecture on, but there was a supplemental video on that. And we've looked at this electronegativity difference. We've already looked at that. But let's see how this plays out. So we've talked about these numbers. So if the difference is less than 0.5, purely covalent, above 1.7 or sort of that range, we call it ionic, looking at electronegativity differences. In between there, though, that's our range of polar covalent, where our electrons that make up the bond are not shared equally. And we start to get a little bit of a negative charge building up. Remember, our electronegativity trend is that electronegativity does increase left to right and decreases down the periodic table. Sorry, let me just back up a little bit more. So let's just actually keep this slide up for a minute. Actually, I'm going to pause the video for just a second. You won't really notice it, but I'm going to pause. Okay, sorry about that. And so let's just, again, sort of think about what that means, these differences in electronegativity. If we're between 0 and 0.4, then we say it's totally covalent and the electrons that make up the bond are completely, utterly shared equally. As we start to get in between that 1.7 and 0.5 range, now we're saying that the molecule of the greater electronegativity is starting to kind of look negative. And that's what this delta negative means here. So lowercase delta, this delta negative means that in this case, in HF, our electronegativity difference is 1.8. And so we're starting to build up, and this actually would be considered close to ionic, to be honest, but we're going to just look at it as polar covalent. Our electronegativity difference is such that the fluorine here starts to look a little bit negative, as opposed to an electronegativity difference of 3. Okay, now we've got full-on ions forming. The atom's going to attract the electrons so much, it's just going to steal one. And so, okay, that's enough about talking about differences. Let's just take a look at, okay, let's come over here now. Let's actually start to look at, let's look at our CH3Cl here. So what we're going to do here we go. When we have a molecule like this, when we have any sort of molecule, what we need to do is we need to start looking at all of the different bonds within that molecule to determine if any of the bonds are polar or not. And so we're going to look at our differences in electronegativity. Let me just bring up the entire electronegativity slide again. Here we go. So, and you'll have numbers like this. So on an exam, you don't have to memorize the electronegativities. I will be providing you with these numbers. You do need to know the trend. You'll need to be able to look at the periodic table and say, and just know, for instance, that chlorine is more electronegative than selenium based on the fact of based on this trend of electronegativity. But when it comes to actually needing to know the numbers in order to determine if a bond is polar or not, you'll be provided with these. So don't worry about that. What we're going to do now, though, is we're just going to look at each of these individual bonds in CH3Cl. And so let's take a peek first at each of the 3 CH bonds. We look at our difference in electronegativity, and signs don't matter here. We're always just going to subtract the larger from the smaller. And so carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.2. So a difference only of 0.3. And so we say that this is a non-polar bond. One of the atoms is not hogging the electrons any more than another one. So all of these three bonds here are what we call non-polar bonds. Now let's take a look, however, at our CCl bond. Chlorine, with its electronegativity of 3.2, carbon with its electronegativity of 2.5, now we have an electronegativity difference of 0.7. An electronegativity difference that's 0.5 and above indicates to us that this absolutely is what we call a polar bond. And so we have a polar bond in this molecule between carbon and chlorine. And so what we have to do, ultimately what we want to find out, is if the entire molecule is what we call polar. Is there a region in this entire molecule where electrons start to build up a little bit? And in this one, there absolutely is. We draw dipoles. We're going to draw in what we call a bond dipole like this. We're going to draw an arrow towards the more electronegative atom, and we're just going to cross it towards the more positive atom with the smaller electronegativity. This tells us that these two electrons here that are making up this bond are drawn more towards the chlorine. They're drawn in this direction, going towards the chlorine. Now, again, let's think about what that really does. What that's going to do is create this region around the chlorine that's kind of sort of a little bit negative. It's going to create another region now around the carbon that's kind of a little bit sort of positive. So we're getting this effect going on here. Now, what we finally have to do is take into account the whole entire molecule and look at all of the different poles in there. Sorry, let me just find, what do I want here? To see about where we're at. Okay. And so we have to look at all of the different polarities in the compound, because sometimes polarities might cancel each other out. And so we have two different polarities that we think about. Our bond polarity, where we just look at all the individual bonds and we determine if the bonds are polar or not. Then we have molecular polarity, where we determine if the overall molecule is polar. If the different bond polarities do not cancel each other out, then we consider the whole molecule to be a polar molecule. And so, sorry, just activated my screensaver. There we go. Isn't that pretty? There we are. Okay. So in this case here, our CH3Cl, we only have one bond dipole in there. There's nothing that would cancel that out. And so we would say that this overall molecule, the whole molecule here, is a polar molecule. There's a region in the molecule where electrons are building up a little bit more than in other regions. Let's take a look at the example of water, which is shown on your screen here as well. So in water, so remember our Lewis structure just looks like this. When determining bond polarities, what we want to do now is move away from the Lewis structure and not even bother to draw in the lone pairs. So this is our correct Lewis structure for water. We have to have the lone pairs if we're looking at just the Lewis structure to determine our electron and our molecular geometries. But now when we're trying to determine if the whole molecule is polar, we're not going to worry about our lone pairs. And we want to try to redraw this, or at least think of this, taking our molecular geometry into account. We know that our molecular geometry here is bent. And so we're just going to redraw the molecule with that bent shape. And now we're going to consider the electronegativities of oxygen and hydrogen. I don't remember them off the top of my head. That's not it. Which slide am I in? Sorry. I'll come back to 114. Let's just go back and look at our electronegativity. So the electronegativity of oxygen is 3.5. Hydrogen is 2.2. So we have an electronegativity difference that does make the bond polar, large enough to make the bond polar. It's going to be pulling towards oxygen. And so we're going to draw both of those in. So those are our bond dipoles for water. Sorry, I'm just unhappy with that arrow. There, much prettier arrow. Now what we want to think about, though, is the net effect of those dipoles. For those of you that have taken physics, think vector analysis. For those of you that haven't, you can sort of start to think about these dipoles as forces that are pulling. If I have, for instance, so if you can see my arms here, if I have my arms out like this, and so both arms going forward, but they're both sort of out to the side. If I'm now being pulled, if somebody's pulling on my arms, hopefully not enough to pull my arms off, but what direction am I going to move? I'm going to move straight forward, right? It's because both of them are pulling me forward, so that's going to give me a forward direction. But the side-to-side direction of this arm is going to be canceled by the side-to-side direction of this arm. And so that's not really what's happening here. We don't have forces pulling, but that's a way that you can think about this analysis. And so the net effect, the overall effect of these two bond dipoles is going to be a net dipole going straight up. And remembering that these in red, those are bond dipoles. And so we make a distinction then between, there we go, between bond polarity and molecular polarity. Because there will be cases where we're going to have bond dipoles, but we won't have a net dipole. Let's take a look at that. And so here, carbon tetrafluoride. I'm not going to draw my lone pairs around fluorine because they're not going to come into play here for our discussion of polarity. If we redraw this, try to redraw this a little bit three-dimensionally, using our dash wedge notation, it would look something like this. Now remember that's what we're talking about. Shape that looks like this. And so let's look at our polarities here. Absolutely, and I don't remember the numbers off the top of my head, but absolutely there are dipoles that exist here between all of the carbons and the fluorines. There's a fairly large electronegativity difference there. Actually, I do remember them off the top of my head. Fluorine has electronegativity of 4, carbons is 2.2, very large electronegativity difference. And so we absolutely have bond dipoles between each carbon and fluorine atom. Let's think about the net effect of these, though. So if we think about maybe just these two right here, we have a bond dipole pulling this way and a bond dipole pulling this way. And so that would be, maybe I'll go in green here. So the red is our bond dipoles. Now I'm just starting to draw the net effect. And so these two atoms here, I'm looking now at this bond dipole and this bond dipole. The overall effect of the two of those is going to be to pull in this direction. Now let's look at the overall effect of the two of these. The two of these are going to pull in this direction here. And so these two are going to pull this way. And so we start to quickly see that the dipoles, all of the bond dipoles here, cancel each other out. So the bond dipoles cancel. And so this overall is a nonpolar molecule. The bond dipoles are canceling each other out. And again, let's think back to what a dipole really is. A dipole is an area in the molecule that has a buildup of negative charge due to a difference in electronegativity. In the case of something like CF4, yes, we absolutely have some electrons being pulled out, but they're being pulled out equally in all directions. So there's no area in this whole molecule that has a buildup as compared to another area along the outside. We're looking at the outsides of these. So electrons, remember, are going to be in sort of constant motion. So they're all being pulled out, and so we're going to have sort of like this cage effect almost of electrons surrounding this whole thing. And there won't be an area in that cage that has a buildup compared to another area. So it is a non-polar molecule, even though there are polar bonds in the molecule. That is an important distinction to make. And here we can start to really see the effect of that. So in this case, we have 3 different cases where we have 3 atoms surrounding our central atom. 2 of these are trigonoplanar. So BF3, and this would be, we have CCl2O. So BF3, we absolutely have polar bonds, but what we can see is that those polar bonds are going to cancel each other out. It's a trigonoplanar molecule. Would look something like this. So trigonoplanar, here's our fidget spinner. So it's a trigonoplanar molecule. And we can see in red, those are our areas of higher electron density. And we can see that they're pretty much evenly spread along the whole outer part of the molecule. Here, now we have the same sort of shape. It's still trigonoplanar, but we have a greater pull towards the oxygen. We have a bigger electronegativity difference here. If we're thinking in terms of our sort of looking at our analysis here and looking at sort of a vector analysis, and I'm not going to bother to draw in the double bond, but we have a situation like this, where now we have a bond dipole here, a bond dipole here, but a much larger bond dipole here. So overall, we'll have a bit of a dipole throughout the molecule. And then finally, NH3. So again, sort of thinking about our overall 3-dimensional shape in NH3. 3-dimensional shape looks something like this. If we look up our electronegativities, we see that we definitely have a pull from hydrogen towards nitrogen. So we have an overall dipole in this molecule. These 2 we can consider sort of canceling each other out, but overall there's nothing left to cancel this one out. So we have an overall dipole in this molecule, making this a polar molecule. And so that's really what you have to look at when you are looking for trying to determine if a molecule is polar or not. So lots of things to put together. And so you might be given, for instance, nothing more than just the formula of a compound and asked to determine, is this polar or not? And so the first thing that you're going to do, let's say we have CH3Cl. First thing that we're going to do is draw our Lewis structure. So we're going to get CH3Cl. We get this for a Lewis structure. We determined that our electron geometry is tetrahedral. Our molecular geometry for this one is also tetrahedral. Then we need to investigate our bond dipoles. No bond dipoles here between carbon and hydrogen. We do have a bond dipole here that is not canceled out. Tells us that this absolutely is a polar molecule. I can't spell molecule today. As opposed to if we're maybe given CO2. Okay, now we're going to draw out our Lewis structure. We get this. We determined that both the electron domain and molecular geometries are linear. We look at our bond dipoles. We definitely pull from carbon towards oxygen, but these two are going to cancel each other out. Therefore, the whole molecule is nonpolar. And so I think we're going to pretty much stop there for today. Let me see if there's anything more that I really... No, nothing more that I really want to go over. But go ahead and try these examples in here. And so try to find out if, or what the shapes and polarities of each of these different molecules are. So try these, PCl3 and BCl3, BCl5 versus SbCl5 2-. Remember to take the charges into account in your Lewis structure. Go through these in practice. Try to find the shape, try to find the polarity, ultimately trying to find out if the molecule is, the entire molecule is nonpolar or polar. Try those out, see what you can come up with. And as always, if you have any questions, feel free to shoot me an email, let me know. But that we are going to end there for today. And so just to recap, what we've really covered is we've looked at using our Vesper chart to determine the electron geometry and the molecular geometry using a Lewis structure. And then using that Lewis structure and the molecular geometry, along with the electronegativities, trying to determine what polar bonds exist in a molecule. And then finally, analyzing all of those polar bonds together to determine if the entire molecule is polar or not. We will be using this idea a lot in some upcoming units to really start to look at the properties of some compounds. This is going to be this idea of polarity and molecular shape. This is key to determining things like boiling points in respect to each other. If we look at something like methane, for instance, compared to water, both about the same molecular weight. Their methane's molecular weight of 16 AMUs, water's about 18 AMUs. Pretty darn close in molecular weights. Methane is a gas at room temperature. Water is a liquid at room temperature with a very high boiling point. And it comes down to the various polarities giving rise to some of these properties. So this is going to be pretty big for us moving forward. And so that is it for today. I hope everybody has a great day, and let me know if you have any questions. I say goodbye, and Rangeley says goodbye.